And so it's technologies like timer coalescing that help the idle scenario, but it also helps during active workloads to really optimize Windows 7 for the Intel hardware, right? And it allows us to make use of the new power-saving features that are being delivered by Intel, both in the processor and system-wide. Okay, let me jump in and over to this system and give you a specific example. I'm going to open a trace. So in Windows 7, and we started this in Windows Vista and have enhanced it in Windows 7, tracing is built into the operating system. And we can turn this tracing on during beta and during RC, and when we're in the lab, we can really juice it up and collect lots of tracing information about what's happening in the system. And we use this tool, which is Expert View, as part of the Windows Performance Toolkit. This is a version that actually hasn't been released publicly yet. It's a version which we've been using during the development of Windows 7 and sharing with some of our deep partners such as Intel. And what's different about this tool, I'm going to work off my screen down here, and I'll explain what you're seeing here. This tool has the ability to trace power as well. So let me start at the top. The top graph that you see here is the actual utilization of the processor, so how utilized is it on a scale of 0 to 100%. This next scale down shows the CPU frequency, so the speed stepping technology in an Intel processor, which allows it to gate the frequency and the voltage. This is showing us what that processor is actually doing during this workload. The next graph down is the idle states. So I talked about C6. There are other power-saving steps that get you down to C6. And we can actually see for each of the processors that are part of each of the cores that are part of the processor, we can see what state we managed to get it into. And then the next several graphs, I have a hardware voltage, hardware current, and then what results in, if you multiply those together, we end up with hardware power. And all these different lines represent various parts of those instrumented systems that you see out in the hallway. So we literally, what we can do, if we want to have a little bit of fun and do some analysis here, is we can take, let's go up to the CPU frequency here. I can zoom in on a section here that's relatively idle, and I can say, hey, let's go and overlay over this graph. I can go down to hardware power, and I can say, let's overlay the power that's coming out of the power brick of this system. And I can overlay any other power for, say, the bus that connects the SATA bus to the hard drive, or the bus that's connecting to a USB device. And so we can get very fine granularity with this tool. I didn't go all the way down to show you that we also get things like disk activity, and we also get things like, if I get further down here, we also get what software is running and what events are happening in software. But what this tool allows us to do is really understand what's happening in the hardware with the Intel's instrumented systems, and also what's happening in the software, and we can get together and have a conversation about those things. So, during any period of time, we can say, hey, what woke the system up during this time? We can go in and, if I go to the summary table here, we literally can look for each CPU. We can figure out exactly what. This is a bad example because I didn't get the power. Let me go down to where I have power. I can drill into a specific area of power and get a summary table. And now I see each and every part of the system, and I can expand it to say, okay, for the Cantiga chipset, let's look at what the instantaneous power is during this trace, and let's look for what it's doing, etc. So very powerful in terms of a collaboration tool. What I wanted to just quickly do is circle back around to that timer coalescing that we talked about, and also some of the tuning we did. You can see, let me just zoom back out here. You can see at the beginning of this trace, so we have about a 30-second trace that we've taken here. The beginning period is, we have a period of relative idleness where the system is very idle, and then we created a workload, the user launched an application, started doing things with the system. But during this period of idleness, where I talked about the importance of understanding how we keep the system in idle and keeping it as efficient as possible, what we can do is not just go down and look at the frequency, because as I mentioned, we want to keep the CPU down at low frequencies and voltages to save power, so we can drill into issues there. what we actually do with that information is we tune what we call our P-state engine, or our power policy parameters in Windows 7. So for Intel processors, we have a unique set of parameters which say, tweak the, the operating system doesn't tell the processor to throttle up to a higher step in the speed stepping unless we determine that, yes, the workload is such right now across the cores that we want you to step up to the next power level. So this policy engine is something that we tweaked over time to figure out, what is the right balance to make sure that during DVD playback we're in the right speed step in the Intel processors. If we jump down, I'm going to just jump down to the idle states. So this graph that's up at the top right now is the CPU idle state. So again, we want to get it down into these ACPI C states and the Intel C6 deep power down state. What we can do is we can drill into these sections to try to figure out, hey, what's actually happening in here. We can go and compare overlay data on what's creating timer ticks. And the result is we can find the culprits that are taking the system out of the deep power state. And the result, I wanted to give you sort of this is an example of some of the data we worked on together during Windows 7, where if you compare Windows Vista for a workload and the exact same workload on Windows 7, on multiple builds of Windows 7 as we progress, what this chart shows is the amount of time that the system was able to stay in that deep power down state. And you can see that with Windows Vista, we were never able to get, this is an accumulative chart, so 10% of the time this core was waking up 1 to 10, or staying down in sleep 1 to 5 milliseconds, and over in the core 42% of the time between 15 and 20 milliseconds. Well, even with the earlier build of Windows 7, we managed to get rid of some of those culprits which were keeping the system from staying idle longer. And what ends up happening is we have instances where we're going all the way up to 50 or 100 milliseconds in that deep power down state. And that's good because there's a cost for getting out and into that deep power down state in terms of time for the processor. But we improved it using telemetry and working together. We managed to improve it that in a later build, we're able to push the entire graph. The blue bar is one core, the red core is the second core, if you're wondering. We managed to push it out so that we got to stay increasingly longer were we able to stay in these longer idle periods. The result for this particular workload is, well, we were showing, I think we actually ended up at close to 20% or more battery life. That's the result for an end user. Right? So, in summary, I think energy management is sort of one of those examples where a very disciplined approach, using the telemetry, iterating on our products and sort of utilizing the features that Intel's bringing to market with Windows 7, we were able to deliver for the end user. Okay. So this chart shows an example of sort of the results. So this is actually for an earlier Montevina reference platform that we had in the lab. On this specific setup, I told you that mileage varies. On this specific setup, with the components chosen, etc., we ended up at 11% power savings for DVD and 2.8% for idle. So it really varies. This is a more modern platform that we have here, so we were able to take advantage of better power down states, etc., and this is a shipping platform where they've done optimization.